Hello, my name is Ali Gambari, and I'm presenting our work on patch correctness assessment in automated program repair based on the impact of patches on production and test code. Test-based generate and validate automated program repair techniques usually take a similar set of steps to fix a given buggy program. They first apply an off-the-shelf fault localization technique to find program elements that are most likely to be the root cause of the bug. Then the most suspicious program elements are transformed so as to generate a set of patches. The generated patches are validated using the available test suite to find the ones that pass all the test cases. We call such patches plausible fixes, as the correct fix for the bug will be among one of them if there are any. Finally, the set of plausible patches are post-processed to present them to the user in a human-readable way. Test-based automated program repair tools suffer from a problem commonly referred to as test suite overfitting problem. This is because test cases usually partially specify the desired behavior of the system, and the patches that pass all the test cases in the validation step are not guaranteed to comply with the specification of the software. Such patches are commonly referred to as overfitting patches or incorrect patches, as opposed to correct patches that actually fix the bug. Due to theoretical limitations in semantic equivalence reasoning, plausible patches must ultimately be inspected by the user to find and apply the correct patch. This is why, in practice, many of the patches happen to pass all the test cases without fixing the bug, thereby making automated program repair tools less attractive from the point of view of software production. To alleviate overfitting problem in test-based program repair systems, patch correctness assessment uses a variety of static and dynamic program analysis techniques to identify likely correct patches. Patch correctness assessment techniques can be categorized into three classes of static, dynamic, or hybrid. Static techniques are usually less precise but can be applied before and after patch validation phase. On the other hand, applying dynamic and hybrid techniques makes much sense after patch validation phase in the program repair pipeline. Patch correctness assessment can be in the form of ranking or classification. In ranking, patches are sorted based on their likelihood of being a correct fix for the bug, and the user goes over the ranked list from top to bottom to find and apply the correct patch. While in classification, the patches are classified into two classes of likely correct and likely incorrect patches, and the user needs to inspect the patches in each class, searching for the correct patch. So far, many static and dynamic patch correctness assessment techniques have been proposed that form a spectrum of manual to fully automated range of techniques. We propose a novel technique named shibboleth for patch correctness assessment that can be used for both ranking and classification. The basic idea behind shibboleth is inspired by the competent programmer hypothesis and the previous research on anti-patterns in the context of automated program repair. In summary, shibboleth expects the correct patch to impact production code less than an incorrect patch and not to decrease code coverage of the originally passing test cases by removing program elements that are already tested and are likely to comply with the specification of the software. To that end, shibboleth captures the impact of patches from three complementary aspects: syntactic, in the form of textual similarity between the original and patched versions; semantic, in terms of behavioral similarity between the original and patched versions; and branch coverage of the originally passing test cases to detect code removals. To understand how these three features can be used to differentiate patches, let's look into an example Java program which is intended to perform a linear search of a character in a string and return true if and only if the character appears in the string. The program has a bug in line number 3, wherein it queries the length of the input string before making sure that the string is not null. The test suite below detects the bug by passing a null pointer to the method. After applying an existing test-based automated program repair tools on this buggy program, we are likely to get many plausible patches. 2 of such patches are shown to the right of the slide. Both patch 1 and patch 2 pass test suite, but only patch 1 is the correct fix for the bug, and a stronger test suite would rule out patch number 2. To quantify textual similarity between the original and patched versions, we use cosine similarity. To that end, we parse the body of the original method and count the number of times each token appears in it. For example, identifiers S, C, and K appear 2, 1, and 2 times respectively in the body of the original method. After applying the correct patch, the frequency of identifiers increases a bit, and we get a cosine similarity of approximately 0.97. After applying the incorrect patch, the frequency of identifier changes slightly, and this time we get a lower cosine similarity. but it is not guaranteed to always be able to discriminate the patches based on textual similarity alone. And that is why we need a complementary feature. As a complementary feature, we use similarity between execution traces. For that, we calculate cosine similarity of execution trace of originally passing test cases. For example, in the passing test case that we had, the original program will execute the bytecode instructions listed to the right of the slide. By counting the number of instructions that we execute, we get 2 instances of A-load, 2 instances of invoke virtual, and so on. After patching the program with the correct patch, the sequence of executed instructions changes slightly, and we get a slightly different number of instruction instances executed from each instruction type. This amounts to a cosine similarity of approximately 0.98. After running the incorrectly patched program, on the other hand, we observe a significantly different execution trace as we have cut off execution and return from the method right after entering it. This results in a smaller cosine similarity, which allows us to discriminate the patches from a different angle. This efficient vector-based behavioral similarity analysis misses out a lot of information, such as temporal relationship between the instructions, details about their types, and so on. We can generate patches that are indistinguishable using both textual and behavioral similarity. To compensate for this, we propose using branch coverage of originally passing test cases to detect functionality removing patches. In the original program, the originally passing test case covers 3 out of 4 branches. After applying the correct patch, 2 more branches are added to the program, out of which 5 are covered. This amounts to an increase in branch coverage. But after patching the program with incorrect patch, while we increase the total number of patches, the number of covered branches decreased significantly, which allows us to detect functionality removing patches. We next present more details about ranking and classification algorithms in Shibboleth. Before that, we need to introduce a couple of functions that are used in the algorithms. The function TS returns textual similarity of the patched and original method bodies. The function SCS returns the behavioral similarity of the patched and original programs. And finally, the function BC returns the difference of the branch coverage of the originally passing test cases between patched and original programs. Here's the ranking algorithm for Shibboleth. I start with explaining the recursive function group and sort starting at line 15, which is the heart of our algorithm. In this part, we cluster the patches into 2 equivalence classes based on a given comparator. For each pair of patches within each class, the comparator returns 0. We also sort classes in a way that representatives for each class are positioned in a sorted manner according to the comparator. Then the classes with 2 or more patches, which are ties, are identified and broken into smaller ties if possible, using the next comparator in our list of comparators. For example, in this particular case, the 2 highlighted classes are non-trivial ties and are to be broken recursively using the next comparator. Let's assume that the first class gets broken down into 2 subclasses, while the other class remains intact. After we exhaust all the comparators in our list, we get worst-case ranking for all patches within each class and present the results to the user. For example, since the first class has A patches in it, all the patches shall receive a rank of A. The next patch receives a rank of A+1 and so on. Classification in Shibboleth is also done using the same 3 features. For each patch pi, we calculate the values of each feature. Together with the ground truth label for the patch, we form a quadruple for each patch, which we use for training different machine learning models. Since for our proposals, random forest classifier performed the best among several other classical machine learning algorithms, we chose random forest classifier as the classifier algorithm in Shibboleth. Shibboleth is implemented using 4,500 lines of code in Java. Current version of Shibboleth target Java programs, but in formulating our algorithms, we did not make any assumption in the target programming language, and the same algorithm should be applicable to programs written in other programming languages with some engineering effort. Shibboleth uses ASM bytecode manipulation framework and Java agent technology to instrument the programs. To minimize the overhead of instrumentation, Shibboleth runs branch coverage and statement count spectra, analyzes concurrently, and it runs only the test cases that cover the patch methods. For textual similarity analysis, Shibboleth relies on Java parser library. In our experiments, we observed that Shibboleth is quite efficient and incurs no sensible overhead on test execution. To perform our evaluation and empirical study, we use patch data from previous work. Specifically, we construct our dataset of patches by combining 5 existing datasets of human-written and APR-generated patches. All these patches target defects4j Java projects. Our APR-generated patches are generated with a diverse set of APR systems, from heuristic techniques to semantic-based ones. We noticed that the initial dataset contained many duplicates, as the datasets are curated by different groups at different times. Additionally, some of the patches were unusable. For example, they resulted in uncompilable programs, or they were not plausible fixes. We eliminated all duplicates, got rid of non-plausible patches. We also removed patches that none of the studied systems were able to support. For example, patches involving file or method creation or deletion that were coming exclusively from defects4j dataset. After this pre-processing, we ended up with 1,871 patches. 778 of them are labeled as correct, while the rest are labeled as incorrect. We use these patches for evaluating classification performance of shibboleth. To evaluate ranking performance of shibboleth, we further removed correct patches that were not paired with any incorrect patches. After this pre-processing, we ended up with 1,290 patches. 197 of them were labeled as correct, and the rest were labeled as incorrect. In RQ1, which concerns ranking performance of shibboleth, we studied the following tools. ObjectSim, which is a dynamic object similarity-based technique that ranks the patches based on the similarity of the system state at the exit points of the patch methods. CIP, which is yet another dynamic patch ranking and classification technique that classifies the patches using a user-provided threshold and scores calculated based on 3 heuristics. An OKI-based ranking that uses OKI suspiciousness values of the patch methods to rank the patches. And finally, we used random ranking based on hypergeometric probability to simulate a situation without any ranking mechanism in place. Our second research question is concerned with classification performance of shibboleth. We compared our technique against the following. CIP again, which does both classification and ranking. PatchSim is yet another dynamic patch classification technique that classifies the patches using a user-provided threshold and a score calculated based on longest common subsequence distance of the execution traces. ODS uses around 1,500 hard-coded features to statically classify the patches. And BERT-LR improves upon ODS by using BERT embeddings instead of engineered features. This table reports top 1 and top 2 performance of shibboleth and other baseline approaches. Here we have all the baseline approaches that are capable of ranking. As we can see, shibboleth consistently outperforms all other approaches. I would like to emphasize that our results are of statistical significance, and we are likely to observe similar relative performance in other datasets as well. Shibboleth uses a combination of 3 features for ranking. We studied the effectiveness of these features using each of the features to rank the patches generated or written for defects4j bugs in our dataset. We summarize our observations in this Venn diagram, wherein each set denotes the number of defects4j bugs for which the correct patch appears in top 1 position. As we can see from this diagram, each feature ranks considerable number of patches in top 1 place that others cannot, suggesting that these features are complementary to each other. To summarize our observations in RQ1, shibboleth ranks a correct patch in top 1 or top 2 positions for 66% of the bugs, and it outperforms state-of-the-art patch ranking techniques. And shibboleth features are complementary to each other in patch correctness assessment. In RQ1, we find the best machine learning algorithm for classification in shibboleth and compare it with the state-of-the-art patch classification techniques. This table reports the results of 10-fold cross-validation for each machine learning algorithm. As we can see, random forest performs the best, and we use that as the underlying model for classification in shibboleth. We compare classification performance of shibboleth with the state-of-the-art static and dynamic patch classification systems. Since we could not apply all these techniques on all our dataset of patches, we had to reuse the published results for 130 patches from one of previous studies. We subtracted these 130 data points from our training dataset and trained the random forest model with the remaining patches. This table reports the classification performance of shibboleth and all other approaches according to accuracy and F1 score. As we can see, shibboleth outperforms all the techniques. To summarize our Q2, random forest is the best model to use with shibboleth, and it achieves an accuracy of 0.89 and an F1 score of 0.85. And shibboleth outperforms state-of-the-art static and dynamic patch classifiers on a dataset of 130 patches.